This is where we left off on Monday, where we had already talked all the way through about factoring polynomials that start with just a 1 coefficient in front of that x squared. And so now we're looking at what happens when we do have a coefficient. And so there's a little more involved technique of factoring these. But the nice part about this technique is that you will definitively know is it factorable or not if you follow all the steps. So we have essentially 4 steps here, and so the first thing we want to do, and let me take an example, and this is very similar to what I just did on the board here, where the first thing that you want to do is you want to take that a coefficient in front of the x squared plus c, that constant in the expression, multiply them together. And so we get 24. Now what we need, according to the second step, is that we need to find factors of this product, factors of 24, that add up to 10. All right, so now you can do a little bit of guesswork here. Sometimes it just kind of pops out at you, like this one was pretty obvious where, you know, what multiplies to 9 and adds to 10? Well, that's 9 times 1 and 9 plus 1. The way you can do this a little bit more systematically is that you start taking all of the prime, or you take all the factors of 24, and you go up to roughly the square root of them. Okay, so roughly the square root of 24 is about the square root of 25, so we don't need to go over 5 here. But we know that we can take 1 times 24 is 24, 2 times 12 is 24, 3 times 8 is 24, and 4 times 6 is 84. Now if I continued my list of factors down here, the next one would be 6, then we would have 6 times 4, so we would be repeating the ones that we had before. So the only thing that we need to do is go up high enough here where if we square this or square the next one, that we're going to get about the number that we're looking at. All right, so these are all the ways that 24 factors, and now we'll add those 2 factors, and you can see 1 plus 24 is 25, 2 plus 12 is 14, 3 plus 8 is 11, and 4 plus 6 is 10. Okay, so then we're going to choose this last one, the 4 and 6, because that equals 10, which is what our b factor is here. This coefficient of x is 10. And then we want to rewrite it, splitting those 2 factors up. So we're going to say, instead of 10x, we're going to say 4x plus 6x. Now, if you find factors that add up to this number, you're guaranteed here to be able to factor this by grouping. Okay, remember when you have 4 terms, you can't always factor by grouping, but here you're guaranteed. And it doesn't really matter if you put it 6x plus 4x or 4x plus 6x, because you'll end up with the same factors. It's just one of those things that works either way. And so now we factor by grouping, and so in the first pair we can factor out an x, and in the second pair we factor out a 2, and then we have that 3x plus 4 group that factors out, and we end up with our factored trinomial. So this seems a little bit longer, I'm sure, than the way we did factoring when it was just x squared plus bx plus c, you know, when we didn't have a coefficient. But if you go through this exercise of making this little table and finding what your number has to be, you know, try and match up that the coefficient of the linear term, in this case 10, this will take care of all the cases. If we don't find it here, if it isn't part of this table, it doesn't factor. You already have a prime factorization with the trinomial there. Okay, so let me go through a couple examples, and I'll put some negatives in there after this first one. All right, so first step is 9 times 2 is 18. Well, 18, that factors only a few ways. That's 1 times 18, 3 times 6, or 9 times 2, right? And so if we say, well, we notice that 3 plus 6 equals 9, and 3 times 6 equals 18, that's how we break up the middle term. So into this 3 and 6. So we got 3x plus 6x in between the 2x squared and the 9. And now we factor by grouping. And so we factor out an x and a 3 from the first and second pairs. And then we notice we have a 2x plus 3 that we can factor out. And so we get that as the factorization. Okay, so let me try one with negatives now. Negatives work the same way, and it's the same rule that we had before about when you have negatives, what is negative, what's positive, and all that. So the first thing that we'll do is we'll take 7 times negative 2, and we get negative 14. Okay, so we know since that's negative and the middle term is negative, since the negative 14, or this last term, is negative, we know that we're going to have opposite signs. And so we know that the one with the larger factor is going to be negative. So if we look at negative 14 times 1 equals negative 14. So we notice here that equals negative 13. And of course, this is the multiplication that gets us that AC. Now we can make that 7x squared minus 14x plus x minus 2. And then we factor by grouping. And then factor out the x minus 2. And there we have it factored. Okay, so in either case, I made that table that I showed you at the beginning. But if you have a number that factors many different ways, sometimes that's helpful. But in this case, it doesn't take too much to figure out, okay, what are the factors of 9 that add to 9? Or in the second case, what are the factors of negative 14 that add to negative 13? Okay, so a couple more examples here. So we have 15x squared minus 11x plus 2. Now, before I show you anything here, look at those signs. We have the plus 2 at the end, so we have 15 times 2 is 30. Since that's positive, that means the signs of the factors are going to be the same. And since the 11 is negative, that means they're both going to be negative. So we're going to look for two negative numbers that multiply to be 30. So we notice that if we say, okay, 15 times 2 is 30, and we're looking for something to add to a negative 11, that makes negative 6 and negative 5. Okay, so that all works. 15 times 2 is 30, negative 6 times plus negative 5 is negative 11. So I'm going to write out my my polynomial in 4 terms instead of 3 now. And then I'll factor by grouping. And I get 5x minus 2 times 3x minus 1. All right, so let's take a look at another one here. Okay, so negative 12x squared plus 5x plus 2. There should be a red flag, not really a red flag, but something to alert you that you need to do something before we look at factoring by grouping. We have that negative 12x squared. Let's make that negative positive. And so the first thing I'm going to do is factor out the negative 1. And now I have this group in parentheses that looks a little bit more familiar to us because it has the first term is positive. So I'm going to factor what's inside the negative and then make sure I retain this negative out in front of everything just to make everything right ultimately when I have it fully factored. So 12 times negative 2 is negative 24. The fact that that's negative means that the signs are going to be opposite, and then we're going to try and get to negative 5. And since that's negative, the larger of the factors is going to be negative. Yes?
So you factored out the negative, so I'm confused on how you got negative 2.
Because when I factor out the negative, this positive goes negative, and this positive goes to negative. So now we have this.
To factor it out and then solve it. And
Yeah.
then start the 4 steps.
Right. And we're going to remember that we have this negative, so when we're all done, we're going to put the negative in front of it still. Okay, so we're just going to carry forward this factor of -1.
I thought we like distributed the negative.
Well, if we distribute it, we're back to this point here, which isn't going to be helpful to us.
Oh, okay.
Follow this to the end, and then re-ask your question again if it isn't clear by the end then, okay?
Okay.
All right. So I noticed that -8, or yeah, 8 times 3 is 24. -8 plus 3 is -5. So this is the combination that I'm looking for. If I multiply these two, -8 and 3, I get -24. If I add the two together, I get -5. So I'm going to rewrite my polynomial. Now, notice here I'm keeping that negative out front. Okay, so this is just carrying forward with us. All right, so I'm going to factor this by grouping. So in the first pair, I factor out a 4x. In the second pair, that's 3x minus 2. There's nothing to factor, so I'll just put parentheses around it. But notice now I have my 3x minus 2 in two groups. And so this factors out as 3x minus 2 times 4x plus 1. But since we factored out that negative stays in front through the whole thing. Okay, so that just carries forward. Yes?
Okay, so this is where I'm just confused because when you rewrote it,
Mm-hmm.
and now it's -5 and -2, how come you keep the negative on the outside?
Because I'm not distributing anything. So I have 12x squared minus 5x minus 2. I'm going to replace this -5x with -8x plus 3x because right here.
Right.
So I haven't changed anything. This negative is still factored out. If I distribute this, I'm going to end up with a -12x squared here, and I don't want that. I want to keep this x squared term coefficient positive, so I don't distribute it. Because if you distribute that negative, it's going to have to apply to each and every term, not just the ones that are negative.
Right, so like to me it looks like the very first step that you did,
Mm-hmm.
equal sign, it looks like you distributed it but then left the negative sign outside parentheses.
Because it's
Well,
a -2.
Yeah, I
12
factored
times
out
-2.
the negative. So,
It's okay, you don't have to explain it, you can just go.
okay, well, come see me in office hours if it's still not clear to you after you review it, okay?
Oh, quick question.
Yeah.
What I'm wondering is, okay, so I know -8 plus 3, works because, adds up to -5, but like, isn't it supposed to,
So then,
like, it can't multiply up to -2, so what, like?
It's not -2 that you're looking for. What you're looking for is -24. Remember, it's the first term, this A times C,
Oh, right.
which is what we're looking for. So that's the -24. That's the adjustment that we have to make to factor this way.
Okay, I think I understand.
that's 5x and plus 2.
Okay.
So then you can negative, the negative's outside.
Okay, so let's move forward a little bit. Okay, so you should try these. Or try this one. This one's all positive, so it's all positive.
So that's just.
Okay, so the first step then is to do what? Multiply 5 by 9. And then notice that we're trying to get to 18. So we have 15 plus 3 is 18. Okay? And so we rewrite it. Factor by grouping. And then factor out the x plus 3. And there you go. Now, to repeat what I said on Monday about these factors, it doesn't matter what order you write these in. You could write 5x plus 3 and then put the x plus 3 on this side as well. There's no standard way to do that. Okay, try another one here. This one has a negative in it. All right, let's see what this one is. 12 times 15 equals 180. And then probably the first thing to try in factoring is always look for the really obvious factors. And to me, 180, the obvious ones are 18 and 10. And if you add those up, you get 28. Okay, so this stands out. So you know that they're going to be the same sign because it's plus 15. You know they're both going to be negative because we want a negative 28. So we have negative 18 and negative 10. Writing that as 12x squared minus 18x minus 10x plus 15. Factor out 6x from the first two and factor out a negative 5 from the second two. Now here's where it takes a little bit of insight to see that when you factor out the negative 5, you're going to get 2x minus 3. So remember that since we're factoring out a negative 5 from this 15, it becomes a negative 3. Now if you get two pairs like this 2x minus 3, and this one doesn't match, chances are you've done something wrong. Not chances are, you have certainly done something wrong. Because this method, once you find these two things, these two facts, this 180 and these two things that equal the b term, this minus 28, this is guaranteed to be able to factor. So these should be the same. And in fact, knowing this first term, you can kind of see, okay, how do I get to that 2x minus 3 by looking at this? And you say, okay, negative 5. So then we'll complete that by factoring out the 2x minus 3, and we get 2x minus 3 times 6x plus, or 6x minus 5. Those are relatively large numbers, and generally when you've seen factoring before, you probably haven't dealt with numbers quite that large. But this method, it works and it's straightforward. It's worst case scenarios, you have to make that little table of all your factors that multiply to 180 and see what they add to. But that's the longest it would take. But it gets you there every single time. Okay, so it doesn't matter which one of these you put first. Like if you said negative 10 minus 18, here notice I've changed the order of these. Instead of negative 18 and negative 10, I have it the other way around. It still factors by grouping. And so you get essentially the same thing. It just commutes. You just get the reverse order, but the same factors. Okay, so let me recap factoring, because this is the end of factoring. Number one, always factor out the common monomial. That is one of the best things that you can do. And if it has a negative, you want to perhaps factor out the negative 1. So if that leading coefficient is negative, factor out a negative 1. Second, what you want to do is look for the special forms. Okay, and so there's a number of those. We have the difference of squares. We have the sum or difference of cubes. And we have perfect squares. Perfect square trinomials. So this is of the form x squared plus 2x plus 1. Those kinds of things. Okay, so once you are convinced that there's no special forms, if you have 4 terms, factor by grouping, or at least try factor by grouping. If you have 3 terms, a trinomial, then and a is 1, you want to try factors of that constant term at the end. And if a is not 1, then try factors of a times c, the first coefficient and the constant term. And then you use factoring by grouping to complete that out. And number 5 is keep factoring. Okay, we had that example on Monday where we had x to the 4th minus 1. That's a difference between 2 squares, so that factored out to x squared plus 1 times x squared minus 1. Well, okay, that's not done. You still have to look at the terms and say x squared minus 1, then further factors. So It's possible that once you fully factor it, or once you go through these steps, that you have additional factoring that you can and should do then. So you want to get it down to prime factorization. Yes.
So on the homework, there was one that had x cubed.
Yes.
So have we learned how to deal with that?
Yes. X cubed are those two, well, why don't you give me the whole polynomial?
X cubed minus 2x squared minus 15x.
Okay, so first rule is factor out the common factors, the common monomial factor. So you can factor out an x here and get x squared minus 2x minus 15, and then you factor from there.
Okay, and then there was one that was like s squared minus 2st minus 24t.
Okay.
So there's like two squares on
Yeah, and that's okay. So you have s squared plus 2st plus t squared?
24t squared.
24t squared.
Well, actually, they're both minuses.
Yeah, I
Not
was
that
just,
it probably matters.
it does matter because that's not factorable.
Oh, okay.
Okay, so when we have this, it's exactly the same thing. Okay, so one of the ways that you can do this, if you have this t and t squared, is kind of ignore that. Okay, and then just try and factor s squared minus 2s minus 24, and then put the t in on the second term, or everything that we talked about still applies to these. For example, if we take the factors of 24t squared is going to be, since they're negative, they're opposite signs, and you want the difference to be 2t, okay, because we're looking at 24t squared. You can do it that way, all right? So if we look at 24 is going to be 2 times 12, or 3 times 8, or 4 times 6, and here's a difference of 2, and so we know then that the s isn't going to have a coefficient because that's a 1, and the difference between 4 and 6 is 2, and these are negative, so they have to be different. So we have a negative and a positive. The larger one is negative, so we have a negative 6, but we also need the t here then, and then we have plus 4t, and so that's the way that factors. So just keep track of the t's and don't leave them out, but you're still looking for the coefficients to work out, and because this is t squared and t, it will work out with the additional variable as well. Okay, and if you want to check it, just multiply everything out. Either FOIL it or do the generalized term, and you should get exactly where you started. All right, so we're going to switch now. Why is factoring useful? And one of the things that we can do with factoring is that we can solve equations. We have this thing called the zero product principle. And this says that if we have two things that multiply each other that equal 0, one of them has to be 0. A times B equals 0. Either A or B is 0. Now, it wouldn't be true if we had A plus B equals 0. Then there's a lot of solutions to that, and A and B can be anything, right? So if A plus B equals 0, if A is 1, B is negative 1. So there's no number, 2 and negative 2. There's no particular number that either of those have to be. But when we have this multiplication, one of them has to be 0. So this is how we're going to solve polynomials now. Let's say we have this, and we want to solve it. Now, you may be tempted to divide by x here, okay, and you don't want to do that. What you want to do is you want to put everything on one side. So it equals 0. So then once everything's on one side, you factor it. Okay, so let's factor it. The first way we factor it is we factor out an x. Now we have 3x squared minus 5x minus 2. You know how to factor that. You take 3 times negative 2, and that's going to be negative 6. And we want two factors that multiply to negative 6 that add to negative 5. So that's going to be negative 6 and 1, right? And so I'll do my factoring by grouping here. And keep going until I get it fully factored. Okay, so what's important here and what's different than everything that we've done so far is that we have this equals 0. Before we were just looking at polynomial expressions, now we're looking at equations. And so we have this equal to 0, and I keep my equals 0 all the way down to this point. So I have this equation now, and notice there's 3 factors, x, 3x plus 1, and x minus 2. So I have 3 possibilities that either the x is 0, the 3x plus 1 is 0, or the x minus 2 is 0. And those, in fact, are your 3 solutions to this equation. So it's easy to see if x is 0, the whole thing is 0, because regardless of what these two evaluate when you have 0 here, this is going to be 1 and this is going to be negative 2, but it's all times 0. So this one's true. Let's go over to the x now. X equals 2. 2 minus 2 is 0, so no matter what these things equal, the whole thing equals 0, so our equation's true. Now here, you get used to seeing these, but what we want to do is find where 3x plus 1 equals 0. And so that's how I got that x minus 1/3. So I say 3x plus 1 equals 0, 3x equals negative 1, x equals negative 1 divided by 3. And so there's our solution. And so we have 3 solutions. Just like absolute values, we had 2 solutions occasionally. We had different sets when we had inequalities. Now when we have a product, we have multiple solutions depending on how many, what degree the equation is. Yes?
Okay, so 2 questions. So when you rewrite it to equal 0, you make everything negative?
No, you just bring everything over to this side. So you're going to subtract 5x squared from both sides, subtract 2x from both sides, and so the 3x cubed stays positive.
You actually solve, like, you actually move it over?
Yeah.
Okay.
Yeah.
And then at the bottom, so I get x equals 0, that's obvious. And then 3x plus 1, you do those equations separately and get that answer.
As equals 0, yeah. And then whatever the solution to that is makes that whole equation work right. Because if you stick in a negative 1 here to check this one, or negative 1/3, negative 1/3 times 3 is going to be negative 1 plus 1 is 0. So that makes this middle term 0. Now, of course, the x in this is always the same. And so if x equals 2, if we're going to choose that solution, you put 2 in every one of those factors, but it still equals 0 because this last factor will be 0. Okay, so it isn't that we're trying to find 3 separate x's. We're trying to find 3 solutions where x equals a particular value. Now this is probably one of the most important ways to solve polynomial equations there is. All right, you certainly have heard of the quadratic formula. We're going to get to that. There's other ways to do it, but factoring is really the best and oftentimes the easiest way to find solutions to equations. Okay, so here's one for you. So let's walk through that then. Okay, so what was the first thing you did?
I brought the negative 2x to the other side, so it'll be x squared plus 2x negative 15.
Like that. Okay. And then it's a matter of factoring. That should be a negative 5. Let me see if yeah, negative 5. Okay? This is a whole section in the book this one particular thing that I was just talking about. And I purposely used, on my example, one that was a little bit more complicated than factoring, because we had to do factoring by grouping. This one, the factoring was simple, but you still had to move everything over so you have some expression equals 0. So these things are really difficult to solve if you try and do it any other way. Like, one of the temptations is when you have an expression like this, let's say that instead of negative 15, that said negative 16. All right, so we would have x squared minus 16 equals negative 2x. Don't factor that yet. Okay, don't factor the x squared minus 16, even though you can, into x plus 4 x times x minus 4, because when you bring the 2x over, now you no longer have all factors. You have something factored, either plus or minus something else. So you want to have everything on one side so you get nothing but factors. Okay, so don't make it an equation of sums or differences. Make it an equation of factors first. Okay, so now we're going to go into a new chapter in the book, and we're going to deal with what's called rational expressions. So when we've dealt with polynomials before, you know, we've dealt with addition, subtraction, and multiplication of polynomials. This is going to allow us to do division of polynomials. Okay, so if u and v are polynomials, say any polynomial you can imagine, if you make them a ratio, we call that a rational expression. Now, rational isn't the kind of the meaning of the word isn't what you would normally use in ordinary English. Like you say, oh, that's an irrational person. Like, oh, that's a crazy person. Or that's a rational person. That's somebody who's sane, who can think. In this case, the word rational comes from the word ratio. Okay, so that's the way to remember what this is about. It has to do with a ratio of expressions. Okay, so we have two polynomials, and I'm going to express them as functions. Okay, so we have u of x and v of x. And so we have this function that's a ratio of two polynomial functions. We'll call that a rational function. Okay, so now we have to think in terms of domains. And domains and functions are going to be really important. So we think about the domain is all real numbers. Okay, so we don't want v to be 0. I think that probably needs another. Should be like that. So in other words, we don't ever want to divide by 0. Now the numerator can be 0, because then you have 0 over a real number, and that's a perfectly good value. But anything over 0 is not defined. And so we have to look at this rational function. It has domain restrictions based on what v at x can be. Okay, so let's look at, yeah. Okay, so let's look at an example here. I want to find the domain of this function. F at x equals 4 over x minus 3, and then I want to look at the domain of g at x is 5 over x squared minus 9. Okay, so remember what the domain is. The domain is are all the values that you can put in that function where it'll evaluate into some other value. So, you know, remember our definition of functions, it's that mapping that takes x and makes it into another value. So if we put in this first one, let's say a 0, f at 0, we get 4 divided by 0 minus 3 is negative 4/3. Perfectly good number. However, if we take x equals 3, okay, so f at 3 is going to be 4 over 3 minus 3. That's going to be 4 over 0, and that's not defined. So we have to exclude 3 from the domain. Okay, so x minus 3 can't be 0, and so x can't be 3. And so we'll write the domain in set builder notation, and this is, remember how this goes. This is the set of x such that x is not 3. Now, thankfully we don't speak that way, but the meaning of it should be fairly self-evident. Yes?
Can you just say, like, d equals all real numbers except x can't equal 3?
Yeah, that's one way to say it. Okay, but here I'm expressing it as a set. So, okay, so now let's look at the second one. We don't want x squared minus 9 equals 0. Now, it's hard to do algebra with an inequality there. So oftentimes what we'll write is x squared minus 9 equals 0, and then figure out the values that x is not supposed to be. Okay, so what we'll do is we solve for the x squared minus 9, and by factoring we know that x can't be 3 or negative 3, and so our since x squared minus 9 can't be 0, then x can't be 3 or negative 3, and so we'll write this in set builder notation as x does not equal 3 and x does not equal negative 3.
Wait, so I see parentheses x minus 3, but parentheses x, what is that? Underneath the solve.
Which one? Right here?
Yeah, right there.
Yeah, sorry, that's x plus 3.
Oh, okay. I thought so, but.
Let's see if I can make that a little bit better defined. How's that?
Yeah.
A little better? Okay, now, simplifying rational expressions. We're going to do this like you reduce fractions. So u, v, and w can be real numbers, variables, or any kind of algebraic expression. So if we have uw over vw, that equals u over v, except when v equals 0 and w equals 0. So in other words, v and w cannot equal 0 in order for this to be true, because then we're dividing by 0. And this is, remember, the way we do, we reduce fractions, right? You factor out and then cancel common factors. So let's do it with a polynomial now. Let's say we have this. Okay, so the thing that I want to do here is I want to fully factor the numerator and the denominator. All right. So now what I can do is start canceling terms. See, I have a 4 in the numerator and a 20 in the denominator. So if I look at the way that factors, 4 over 20 is the same as 1 over 5. And if I have an x squared over x, that's the same thing as x. And so my simplified version is this. So this simplified equals this. But we have one issue now. What happens if x equals 0? Okay, so in this case, what we've simplified it to is 0 times this x here is 0 times 0 plus 1 is going to be 0 times 1 divided by 5 is 0. No problem there. But we do have a problem when we make 0 here because we're going to have 20 times 0 is 0. So we have division by 0 in the original expression, but not in the new expression. And so what we have to do is we have to say that x does not equal 0. So this is only true when x does not equal 0. This is what's called a domain restriction, and when you're simplifying polynomials, you must write that down. Yes?
What did you do from step 2 to 3?
From here
Yeah.
to here?
Yeah.
Okay, I have the 4 over 20, and so 20 is 4 times 5. So the 4's cancel, and I just get a 5 in the denominator. In the numerator here, I have x squared divided by x, which just makes x in the numerator. So that's where this x comes from. Okay, I'll rewrite it on the board like this. 4x times x, 2x plus 1, and then we have 4 times 5 times x. Okay, so this is even factored more. Okay, these cancel, and I get x times this over 5.
Why is that a domain restriction?
It's a domain restriction because this is our original expression, and our original expression has a built-in domain restriction where x can't equal 0, because then we'd have 0 over 0, which is undefined. But if we simplify it, now if x becomes 0, well, that doesn't tell the whole story because this now equals 0. It doesn't equal undefined, it equals 0. And so we have to say x can't be 0 because the original expression, x couldn't be 0. So it would be the same then as if we're taking x over x out. If x was 0, we're factoring out a 0 over 0, which doesn't have any meaning. Okay, so any domain restriction that we have from the original expression carries over into the simplified expression, even if that term cancels out. Okay. Now, when you have x squared plus 2x plus 1, it's implied that x can't be negative 1, right? If I look at this expression and I say, what's the domain? I can easily say, yeah, x can't be negative 1. So that's what's called an implied domain restriction, when the expression itself will tell you what the domain is, or what the domain restriction is. Now, if we were to simplify this, let's say if we factored this, and then we canceled that out to be x plus 1, this one loses that implied x does not equal negative 1, so you must state it as a domain restriction. So if I'm just writing this, I just write that. Okay, you can see by the expression x can't equal negative 1 because then you're dividing by 0. So this one has a built-in stop sign if you want to think of it that way. When I simplify it, I get x plus 1, and there's nothing that says x can't be negative 1 because negative 1 plus 1 is a perfectly good number, 0. All right, so you have to state domain restrictions that are not implied. So if my function is that expression, and I simplify that function to this, now these two are the same function. If I didn't write the x does not equal negative 1, they're not the same function because this version of f is defined for x equals negative 1 while this one is not. Okay, so here's the equivalent. Now these two are equivalent functions because we put in the domain restriction. I know that's too fast. Yes?
So, you have I understand why you have the restriction at the beginning,
Mm-hmm.
and then at the end. So you say it loses it, but isn't it still the same?
Well, this one, it's implied, This one, you have to explicitly state it to make it the same as that. You see, this function, f equals x squared plus 2x plus 1 over x plus 1, is not the same thing as f at x equals x plus 1. It only is the same thing or an equivalent function when we restrict the domain.
Okay, so if there's a restriction at the beginning, you have to keep it at the end.
Exactly. And so the implied ones don't have to be stated, but if you simplify something out to take out the implied domain, you have to make it not implied, you have to explicitly state it. Okay, very good. We'll resume this on Friday. Tutorial tomorrow, you will have a quiz. It's going to be on factoring. And then we'll probably, in some of the workshop stuff, do some of this domain restriction business, okay?